So my interest in complexity and simulation stems largely from my background in computing and artificial intelligence and neural networks. And how I get from there to complexity is a neural network is a universal function approximator. If you have a set of data, you can approximate that function to within, the data rather, to within an arbitrary degree of accuracy just by adjusting the numbers of parameters in the neural network. And there's something singularly unsatisfactory about that because you're not really explaining the dynamics that are underlying the data that you have. And so I sort of became interested in the sort of complex systems discourse in the literature, and of course then associated with that agent-based modelling, drawing on some of my experience in artificial intelligence and artificial life. My main projects at the moment are sort of looking at ways of incentivizing different kinds of actors to achieve kind of macro-level policy goals. Some work that I published a couple of years ago, for example, was exploring non-linearities in the relationship between the amount of money you give to farmers under, in Europe, we have the Common Agricultural Policy and incentivization scheme for farmers, and desired biodiversity outcomes in terms of the numbers of species. And so there we've coupled together a model of farm decision-making, where this is influenced by neighbouring farms and experience with using previous land uses, and also, of course, influenced by the market and the climate. But we try different government policies and vary the amount of incentive we give to the farmers and see how much biodiversity we get out as a result. And we showed that there's a highly non-linear relationship there because the government policy, firstly, is not acting in complete knowledge of the ecological system, and also because it's acting in the context of other incentives and drivers of farm behaviour. Other work I've been doing has been looking at ways of incentivizing households to use energy more efficiently, and in particular, giving grants to install more energy efficient appliances and perhaps removing the less efficient appliances from the market. So I've had a number of projects that I've been working on using agent-based modelling to try and explore these more policy-related issues. So at this conference, the main paper I've been presenting is one on comparing two implementations of a social theory of, I should say, in fact, an environmental psychological theory of everyday pro-environmental behaviour. And this is related to work on incentivizing householders to use energy more efficiently for appliances and space and water heating. Now, the interesting thing about that theory is that we drew on it because we had a colleague in the project who was a prominent environmental psychologist, and so we wanted to draw on her work. But she, Linda Steg, who is in fact based in Groningen, had also worked with another colleague in Groningen using her theory to a completely different context, this question of littering. Now, one of the big issues, I think, for social simulation is how we go about formalising theories of behaviour, at any level in society, and in particular how we formalise theories of interaction. And so my paper here was comparing the simulation model of the littering application of goal framing theory and our implementation of it in the model of everyday energy consumption in the home. And the interesting thing is that there are various areas of commonality. We've used numbers to represent certain concepts in a similar way. But there are also some significant differences driven in part by the context in which the models are operating. And I think that in general this offers a way in which agent-based social simulation can both gain from and give benefits to the more conventional methods of of social science, that we can start to force them to ask more detailed questions. You never really realise how little you understand until you try and write a computer program. It makes you ask a lot of questions.